because the sphere of an orbital can only take on one orientation. Right? If I move over to, let's go to something like, let's see, here we go, here's aluminum, right? So aluminum goes 3s2 and 3p1, right? So its outer electron occupies a 3p orbital. Here's the nodal picture for a 3p orbital, right? So here's the nucleus, and it goes from blue to orange. That's one node. All right, 3p, n equals 3, l equals 1, minus 1, 3 minus 1 minus 1 is one node. All right, and so the node is this thing right here. Here's the electron configuration for aluminum. Here's the orbital diagram. Here are the quantum numbers for that outer electron. Pretty cool, huh? All right, so if you want to look at some really wild ones, here's the Ds. See how the nodal pictures get more elaborate? Here are the Fs. Check out, look at the F. This is wild stuff, right? It's like, calm down, right? I tell my kids all the time, quit acting like an F orbital. You're getting out of control. Your energy level's too high. All right, so the 4F is higher than the 6S. Time to relax back down to a 2p orbital, okay? And emit a photon. All right. So check out ptable.com. It's worth like helping you study for the exam. It has just a lot there. So here's a sample problem. Compare the energies of the 3s and the 3d orbitals for beryllium 3+. So we have beryllium 3+. We're comparing two different orbitals in the same atom. So which one is going to be higher in energy, the 3s or the 3d? The 3d will be higher. Simple as that, right? We're in the same atom. If it's in the same atom, actually, you would think it would be higher. Let's think about this now. Beryllium 3+, what kind of atom is that? Is that a one electron atom or a multi-electron atom? How many electrons are in a beryllium 3+ ion? Only one, right? For one electron atoms, are the 3s and the 3d equal or different in energy? They're equal. So what do you think the answer is then? They're both the same energy because it's a one electron atom. Okay. So for beryllium, for beryllium 3+, (3s) is equal to 3d in energy. What do you think it would be if I just said beryllium 2+? Change the problem a little bit. What do you think the answer is? Now we have more than one electron. Now we use the more complicated split levels, right, of how the periodic table normally tells us. So now we can say the 3s is lower in energy than the 3d. Make sense? So again, for hydrogen-like atoms, all the orbitals in a given sublevels are at the same energy. All right. And why is that? Because there are no electron-electron repulsions causing this splitting or screening, as you will. Okay, there's no screening in a one electron atom. Okay. All right, and an electron cannot screen itself. It's just what it is. Let's do another one. Compare the energies of the 2p orbitals in lithium 2+ and beryllium 3+. Just to add a add a little note to this. I'm just going to say 1 electron versus 2 electrons, right? So let's say 1 electron atoms. All right, no screening. Okay. So for this question, 2p orbitals in Li plus and beryllium 3 plus. Okay, how would they compare? Right, they're both 1 electron atoms. So if they're both 1 electron atoms, we're just talking about the 2p neither 1. So what's the difference between them then? They have the same electrons, but what's the difference between them? They have different protons. Which one has more protons in its nucleus? Beryllium, right? So that means a 2p in a beryllium atom is going to be pulled more towards the nucleus than a 2p being pulled towards the nucleus of a lithium ion. Does that make sense? So now we're talking Coulomb's law. So this is sort of like quantum theory, but this is a Coulomb's law argument. Okay, so lithium 2 plus has how many protons in it? 3 protons. Beryllium 3 plus has 4 protons in it. Therefore, 2p in beryllium 3 plus will be lower in energy than the 2p in lithium 2 plus. Here's a pretty easy one. Rank 2s, 3s, 3p, x, and 3d, x, y orbitals of lithium from lowest to highest energy. So now we're just talking about lithium, which is a multi-electron atom, right? So how do you think these how do you think these orbitals compare? So we get 2s, 3s, 3p, and 3d. For multi-electron atoms, think back to this slide, way back in the beginning. So it's this versus that. So all these questions are asking you to go back to this. So this is the diagram for lithium neutral, multi-electron atom, right? So order the orbitals in order of least to highest energy. 2s lower than 2p, which is lower than 3s, which is lower than 3p, and so forth. Okay, so go back to this. So this should be pretty easy. What's the order? 2s. Yeah, 2s is lower than 3s, which is lower than 3p, which is lower than 3d. Does it matter if it's x or y or z here? It doesn't. Does it matter if it's x, y, or z, y? For this, it doesn't. Right? What if it was lithium 2 plus? How would that change the question? Or how would that change the answer? 2s would be lower than 3s, but 3s would be what? Equal to 3p, which would be equal to 3d. one electron atom versus multi-electron atom. So that all this is because of all the screening that goes on. It's screening. If there's no screening, then it's Coulomb's law. But if there's screening, then you got to think about more of the quantum nature of things. So with lithium 2+ versus 3+, these are both one electron atoms, so it boils down to Coulomb's law, right? But with multi-electron atoms, then you got the quantum effects that happen. When you do electron configurations, I've been kind of saying it for a while, but not really specifically pointing to it. We have this principle called the Aufbau principle, which says that when you fill in electrons into atoms, they always fill the lowest energy orbitals first, and they fill up. All right, and that should be familiar from Chem 107. Okay, so you might remember this diagram from high school chem. I put it in the notes here, but I'll tell you right now, I hate having this slide in my notes. And the reason why is because it's so unnecessary. How many of you remember this from high school? All right, yeah, you might remember this from high school. It just says, start filling from the 1s first, then the 2s, then the 2p, 3s, 3p, 4s, 3d, 4p, 5s. It goes in this order. Okay, all this is doing is just veering you off from the fact that you just need to look at the periodic table and read it like a typewriter. Okay, so if I'm looking at the periodic table on the wall there, 1s, 2, 2s, 2p, 3s, 3p, 4s, 3d, 4p, 5s, 4d, 5p, 6s, 4f, 5d, 6p. Right, I'm just going left to right, left to right. That's all I'm doing when I'm looking at the periodic table. You don't need this. But I show it anyway, just in case this is what you were relying on before. I'm trying to get you off the crack and get you onto the... I'm trying to get you off the crack and onto the caffeine. I'll give it just less detrimental to you than crack, okay? I know I use these strong analogies, but I'm just saying, get off of this stuff. Okay, it's not, it gets you away from using the periodic table, which is what you should be using. Okay. It got your attention, didn't it? There you go. All right. So yeah, this is just nonsensical. So for electron configurations, this should be familiar ground for you. We're getting to familiarity for you. That's good. An electron configuration is the complete specification of how an atom's electrons are distributed in its orbitals. So for a 1s1 configuration, 1 is the principal quantum number, in this case. S is the angular momentum quantum number, L, and we were pointing to this already last time, right? I was pointing out that the N and the L. With an electron configuration, they use this exponent with the number that tells you how many electrons are occupying that particular orbital. So here's an example of an orbital diagram for hydrogen. It's the simplest atom. It's got one electron, 1s1, done, right? So for hydrogen, it's simply just 1s, right? For helium, what do you think it would be? It'd just be 1s2, right? And you do this, right? For lithium, it's 1s, then 2s, right? Right, you've seen this before, right? It should be at least familiar to you. And it goes on and on and on. There's another rule after the Aufbau principle called Hund's rule. And what Hund's rule says is if you have to fill a sublevel or subshell, you have to put the arrows parallel to each other first before pairing up electrons. So electrons would rather occupy their own unique orbital rather than having to share an orbital with another electron. Why is that? Electrons don't like each other. They're like charges. They don't want to be close to each other. Okay. Which element is depicted to the right? Which element do you think this is? Pick one from the periodic table.
Nitrogen.
Nitrogen, right? Nitrogen. 1s2, 2s2, 2p3. Right, that's nitrogen. What?
Or you just count how many there are instead.
Yeah, right. I mean, assuming it's a neutral atom, you just count how many arrows there are, and you pick 7 for nitrogen, right? Because number of electrons are usually equal to the number of protons for a neutral atom. Okay, so this orbital diagram here does not show the correct filling, okay, according to Hunt's rule. All right, so this arrow pointing down should be over here. Okay, just to show you the long way to do it. Let's write a complete configuration for antimony. Alright, so SB, antimony. Who knew SB stood for antimony, right? Alright, so let's do the orbital diagram for antimony. Do 1s, 2s, 2p, 3s, 3p. So you should be able to come up with this on your own. You should be able to draw this out. Alright, is it hard? No, it's not. You got the periodic table, right? You just got to read the periodic table, okay? What comes next? 4s, 3d, right? You got 4p. And then what's next? 5s.
4D.
Right. 4d.
5P.
And 5p. That should be good enough for antimony. Alright, so filling this in, antimony has how many electrons in it for a neutral atom? 51, right? So I'm going to fill 51 electrons in here. So how does the last 5p fill? One for each. There you go. It also says write the complete electron configuration, right? So, to put this in the complete configuration, it's just simply 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, 4p6, 5s2, 4d10, 5p3. Let's do shorthand. That's so much less painful. So for shorthand, what we do is we look at the noble gas core and try to bracket that in. So if we take just this part, okay, what would that be? It would be krypton, right? So this is going to be krypton in brackets, and then we have 5s2, 4d10, 5p3. How are we doing? Cool? Easy? Easy peasy? This is just a little bit, you know, well, in fact, a lot like Chem 107. All right, so now here's something that'll be new, but it's kind of cool. Okay, a word on valence electrons. So valence electrons are often defined as electrons that occupy orbitals with the highest possible n value plus those in partially filled d and f orbitals. In Chem 107, we basically said, just look at the highest n value and how many electrons are in there. It's probably a valence electron. We're kind of refining the definition a bit more. So that's the semi-official definition, but ultimately the group number of the periodic table will always define the number of electrons, valence electrons in an atom, except for the F block elements. Right? The F block elements, it depends on what the reaction is. Okay. Do you remember in the transition elements how you can have different charges for the ions? Do you remember that? Just in naming nomenclature, like copper or cobalt could be +2 or +3, iron could be +2 or +3. A lot of the metals, transition metals, a lot of the transition metals and metals towards the metalloids, and also in the F block elements, lanthanides and actinides, they undergo so many different kinds of chemistries that we can't really say for sure, okay, it has this specific number of valence electrons versus not, because clearly the elements are forming different compounds and the valence electrons are changing to make those different compounds happen. Okay, so for the lanthanides and actinides, we can't really say for sure how many valence electrons there are. Okay, but for the D and F block elements, I mean for the D's and the P's and the S's, we can say, okay, these should have a certain number of valence electrons. So the definition of valence and the group number usually do agree, but the transition metals, lanthanides, and actinides do show discrepancies. Okay, and I'll illustrate this. When you look at a periodic table from one source versus another, it drives me batty. Okay, and I'll show you why. Take a look at cerium. Okay, in this periodic table, you look at cerium and it's in group 4b. Okay. Now I'm going to show you a different periodic table. What group is cerium in? 5b. There's no consistency there, right? Okay, so what you oftentimes find is that periodic tables, they'll just throw the F block elements down here below, and they won't line them up with any particular group because of this because of the varying chemistries that these elements can take on. Okay, so I mean, if you try to look online, well, how many valence electrons does europium have? You know, you're gonna have a hard time finding a straight answer. Okay, so now a lot of these heavier elements in the actinides, they have short lifetimes, so they're hard to study. But nonetheless, it's just difficult to pinpoint how many valence electrons there are in the F block elements. But you can get you can come up with an idea if you wanted to based on the definition. Here's another thing that's kind of tough to swallow. The American naming system shows that iron and cobalt and nickel all have 8 valence electrons. They don't go on in it. They don't continue the count. They don't continue the order. Okay, and that's because, and then I've been asked around about it, asked my dean, asked other faculty. None of them can give me a straight answer. So it's not just me. But another colleague of mine who I used to work with, she was telling me that, well, she kind of comes from an inorganic background, has somewhat of a background in coordination chemistry, And she said that the way it's laid out here is because of observed coordination chemistry of the compounds that some of these metals have formed. So, in a nutshell, just for the sake of argument, for the sake of this class, just say that iron has 8 valence electrons, but so does cobalt and nickel. Okay. Now check this out. How come it goes back to 1 again here for a copper? And we'll talk about that. Okay. So we're kind of digging a little more into the nitty-gritty of the periodic table and why it's laid out the way it is, right? So electron configurations for ions. So for an electron configuration of a cation, whatever the positive charge is, you take that number of electrons off, and that's your electron configuration for that cation. Does that make sense? So if I had, for example, what if I had magnesium 2+ versus magnesium neutral? Right? Magnesium neutral is 1s2, 2s2, 2p6, 3s2. What would magnesium 2+ be? It'd just be at the 2p6, right? The 3s2 gets removed, right? So however many, whatever the charge is, you take that many electrons off. Okay. For anions, it's the opposite. If there's a negative charge, you add that many electrons to the neutral configuration. All right. Now here's a new one for you. Okay, for transition metal ions, cations always fill their D sets first before filling their S set with the next N value. Let's do an example to illustrate that. So example, compare the orbital energy level diagrams for Fe versus Fe3+. Let's use a different color. All right, so here's Fe. Let's see, we'll do Fe3+ here. So we got 1s, 2s, 2p, 3s, 3p, and we got 4s, and I'm just going to put 3d over here. I think I'm going to color code this. So we'll use purple for iron, and then we'll use red for Fe3+. Okay, so for iron, let's do this. 1s2, 2s2, 2p6. So according to iron, how many valence electrons does it have? We've got 8 valence electrons, according to the periodic table. So there's 5. So we've got 5 here, and the 2 here, that makes 7. The 8th valence electron has to go there. So 8 valence electrons in Fe neutral. Just to do the 4s and the 3d,